Hey guys, good evening and welcome back again to your Unacademy NEET English channel. I hope all of you are doing great, doing good. So let me know quickly in the chats if all of you can hear me, if I'm perfectly audible, visible to everyone quickly in the chat. Yes. Welcome back, people. Welcome back. Welcome back. So quickly, let me know in the chats if all of you can hear me, if I'm perfectly audible and visible to every one of you. Everyone in the chats. Perfect, guys. Perfect. So as you all must be knowing that today we are starting the new chapter and the name of the chapter is going to be Chemical Kinetics, right? It is one interesting chapter and it's simple at the same time. It's not that difficult. So I was reading your chats. Some students were saying, sir, if we have not completed the equilibrium yet, can we join the session? Absolutely, you can join the session because I'm exactly going to start from the basics only, right? Which I keep on doing always. So this chapter also will be started from the basics, from the scratch, so that you won't be having any issue, any problem in understanding this particular chapter. Yeah? Welcome guys, welcome. Good evening and welcome back. I'm doing good. Thank you so much. Thank you so much. So dear students, one more thing. This chapter, it might take some 2 to 3 sessions to complete, right? Minimum 2 sessions, maximum 3 sessions. Every session will be of the duration approximately 3 hours, right? I'll be covering all the theory as well as all the problem patterns which can be asked from this chapter as far as your NEET, even JEE examination is concerned, right? No, it's not tough chapter, it's easy only. You'll get to know in some time because I'm going to start from the scratch only, from the basics. So imagine as if you have never studied this chapter before, okay? That's my guarantee. After doing this chapter, you'll be able to solve majority, 99% of the questions you should be able to solve on your own. Right? Perfect, guys. So before starting this particular session, the ones who have not liked the session yet, I would want you guys to like the session. Do share this particular video with everyone. Whosoever is preparing for NEET 2024 or even 2025. This particular session is for every single one. Right? And at the same time, the ones who have not subscribed to Unacademy NEET English channel yet, I would want you guys to subscribe to the channel right now. Okay? My dear students, this session duration will be approximately 3 hours or even more, right? 3 hours or 3.5 hours. So just let me know before starting whether you guys are ready to be with me till the end of the lecture 1 of kinetics. Let me know once in the chats, quickly. Quickly, dear students. Quickly. Vanakkam, Balahari, vanakkam. Nice. So let me know quickly in the chats. Everyone. Are you ready? Perfect. So people, whatever I'll be mentioning on the screen, whatever I'll be writing on the screen, I would want every one of you to take a note of every single thing because every single thing is going to be very, very important as far as this particular chapter is concerned. Yeah? Right? So take a note of every single thing. Perfect. So let's get going then. Let's get started with the chapter Chemical Kinetics, right? Chemical Kinetics. First of all, let me give you the brief introduction of the chapter Chemical Kinetics. A brief description about the chapter, like what all things we are going to cover in this chapter. My dear students, this particular Chemical Kinetics, it deals with what? Let me tell you, it deals with the rates of the reactions. Number 1. Number 2, it deals with the factors. It deals with the factors affecting the rates of reactions. Factors affecting the rates of reaction. and at the same time, it deals with the mechanism involved in the reaction as well. Okay? So basically, three things we have to discuss in this chapter. Just give me a second, let me change the pen. Okay. So three things we have to discuss in this particular chapter in detail. So this particular chapter is going to let us know about the rates of the reaction, about the speeds of the reactions. This chapter is going to let us know why some reactions are slow, why some reactions are fast, why some reactions have got the moderate speed, right? This particular chapter is going to let us know the factors on which the rates of the reaction depends and what are the mechanisms involved in a particular reaction. So all those things we have to discuss here in this particular chapter in detail. Perfect. So quick definition of the chapter, chemical kinetics, right? Now, my dear students, before starting the first topic of the chapter, before starting the first topic of the chapter, I would want to write one statement over here. And what is the statement all about? Have a look on the statement which I'm writing over here. The statement is very simple. When the reaction starts, concentration of reactants keeps on decreasing with time, and the concentration of products, it keeps on increasing with time. What this particular statement exactly means, let's try to understand this. Have a look, people. When the reaction starts, the concentration of reactants decreases with time, and the concentration of products, it increases with time. Now, you must be thinking, what is concentration, first of all, right? You must be thinking, what is concentration? Concentration is represented by square brackets. Either square brackets, or you can directly represent it with C. And how do we define it? It is simply defined as number of moles per unit volume. Number of moles per unit volume. Now, what it means exactly? Try to understand. My dear students, for example, you have got the reaction A gives B. Let's assume this is the reaction. A gives B. Imagine that this particular reaction is taking place in a container. This reaction, for example, has to take place in a container whose volume is, let's assume, V liters. Okay. Now, for example, at time t is equal to 0. At time t is equal to 0. Time t is equal to 0 means the reaction has not started yet. That means the reactants have not got converted into products yet. So at time t is equal to 0, in the container, there will be only reactant present because the reaction has not started yet. B has not formed yet, right? Let's imagine that at time t is equal to 0, we have got some 10 moles of A. So therefore, we'll be having some 0 moles of B in the container because the reaction has not started yet. Now, with time, when the reaction will start, when A will start getting converted into B, what will happen to the moles of A? I'll say moles of A will start to decrease. And at the same time, moles of B, it will start to increase. As simple as that. When the reaction starts, moles of reactants will keep on decreasing and moles of products, that will keep on increasing, right? My dear students, if I define the term concentration of reactant, what is concentration of reactant? Concentration of reactant is going to be number of moles of reactants divided by volume of system in liters, right? If I define the concentration of products, it's going to be number of moles of products divided by volume of system in liters, right? Now you tell me one thing. As the reaction starts, number of moles of reactants, that decrease with time. Now you tell me, if number of moles of reactants decrease with time, can I say concentration of reactant will decrease with time? Absolutely. Concentration of reactant is going to decrease with time. In the similar way, as the reaction starts, number of moles of products, that increases with time. And if the moles of product increases with time, what happens to the concentration of product? Concentration of product also increases with time, right? So as I told you, as the reaction starts, the concentration of reactant keeps on decreasing with time, and concentration of product it will keep on increasing with time, right? And at the same time, if you want to have a look over the same statement graphically, you can do that as well. For example, I'm making a graph between concentration versus time. I'm going to make two graphs between concentration versus time. One is going to be for reactants and one is going to be for products. For reactants, we know with time the concentration of reactant decreases. So concentration versus time. As the time passes by, the concentration of reactant is going to decrease with time, right? Similarly, as the time passes by, the concentration of product is going to increase with time. So this particular graph, it is valid for reactants, and this particular curve, it is valid for products. Let me know first of all in the chats if you got to know this particular concept. Quickly in the chats. Sir, voice is not clear. Can you just let me know in the chats if you all can properly hear me? Let me just check it out. Similarly, as the reaction starts, number of moles of products that increases with time. And if the moles of product increases with time, what happens to the concentration of product? Concentration of product so in time. It's absolutely clear, right? Looks like the RJ's voice. Yeah. Okay, is this particular statement clear? As the reaction proceeds, the concentration of reactant will keep on decreasing and concentration of product will keep on increasing. Yeah? Perfect. And these are the two graphs which I would want all of you to remember from now onwards. I hope this particular thing is clear to everyone. My dear students, there is one more thing. There is one more thing which I want to share with you. And what is that particular thing? Let's have a look. Understand. I told you I'll be starting from exactly basics. I don't want you guys to have any confusion in between. Try to understand what I'm going to say. Let's say the state of this A is gas. The state of this B is also gas. Right? Let's say A is in gaseous phase. B is also in gaseous phase. Can you let me know at time t is equal to 0? At time t is equal to 0. How many gases will be there in the container? At time t is equal to 0, there is only A present in the container. There are 10 moles of A in the container. So I can say, initially there is only one gas in the container. Initially there is one gas in the container. Right? Now, as the reaction proceeds, the number of moles of A will start to decrease. The number of moles of products will start to increase. Right? Right? Now people, if I ask you, if the moles of A are decreasing with time, that means particles of A are decreasing with time, right? So pressure due to A is decreasing with time, yeah? And pressure due to B, that's increasing with time. So if I ask you to plot a graph between pressure versus time, for the reactants, what this curve will look like? Since the moles of reactants are decreasing with time, therefore the pressure due to reactant, that will also decrease with time, right? That will also decrease with time. Similarly, if I ask you to make the same graph for the products, pressure versus time, you know, as the reaction proceeds, the moles of product increase with time, hence pressure due to product, that will increase with time too, right? This graph is particularly valid for products, yeah? As simple as that. Whether you want to make the graph between concentration versus time, or pressure versus time, or moles versus time, the nature of the graph will be the same. The nature of the graph will be the same, right? If you are making moles versus time, the nature of the curve will be absolutely the same. So this was the first point which I wanted to share with you, right? Let's have a look on one more thing. Right? This was, my dear students, the first point. Now, let's go into our first topic. Let's try to see the first topic which we are going to cover. I'm starting with a topic that is average rate of reaction. R average. If you ask me, how do we define this R average? How do we define this R average? How do we define the average rate of reaction? Let's try to write its definition. Then I'll make you understand what it exactly means. Try to understand things. Average rate of reaction is defined as, the change in the concentration of either reactants or products. Change in the concentration of either reactants or products in a given time interval. In a given time interval. This is one of the definition of the average rate, right? Well, there are many ways to define average rate. Right now, I'm defining it with respect to concentration. I can define it with respect to pressure, with respect to moles, etc. But this is something which I want you guys to remember. Average rate of reaction, it's defined as the change in the concentration of either reactant or product in a given time interval. Since we have seen that the concentration of reactant decrease with time and the concentration of product increase with time, right? Yeah? Right, people? Someone is asking about something. Let me tell you, these are not one shots which are completed in 1 hour. These are detailed marathons, right? Okay, these are detailed marathons. Every single topic is discussed here. Okay? So someone has come here to text something. So please, you shut your mouth and let others concentrate, yeah? I hope you got it. Okay. So average rate of reaction, it is defined as the change in the concentration of either reactants or products in a given interval of time. Let's try to understand. Let's try to understand what exactly I'm saying. My dear students, before making you understand this particular statement, I'm going to write it in the mathematical formulation. Average rate of reaction, it is equal to change in the concentration, delta C, change in the concentration of either reactant or product divided by time interval delta T. Now, in the beginning, I'm going to use a sign, plus and minus. What is the significance of this plus and minus? You'll get its idea in just few minutes, right? In just few minutes. Try to understand what exactly I'm saying now. See, for example, you have got a reaction A gives B. Let's say you have got a reaction A gives B, for example. Okay. My dear students, let's assume that at time T is equal to 0. The concentration of reactant, for example, is C1. The concentration of product will be 0 because the reaction has not started yet. Okay. Now what is going to happen with time? As the reaction will start, the concentration of reactant will keep on decreasing with time. So, for example, at time T2, the concentration of reactant left is, for example, C2. And the concentration of product formed, that is C3. So, first of all, be careful with the terms which I'm telling. C1 is the initial concentration of reactant at time T is equal to 0. This is the concentration of product at time T is equal to 0. Now, at time T2, let's assume that the concentration of reactant left is C2 and the concentration of product formed is C3. Now, you tell me just one thing. Already we have discussed that as the reaction proceeds, the concentration of reactant that decreases with time. So tell me whether C2 is greater than C1 or C2 is less than C1. I would say C2 will be less than C1, right? Absolutely, C2 will be less than C1 because we know the concentration of reactant that decreases with time. Perfect. My dear students, if I choose this particular time interval, I'm choosing this particular time interval, right? In this particular time interval, the concentration of reactant changes from C1 to C2 and the concentration of product, it changes from 0 to C3. Now, average rate of reaction in this particular time interval, the average rate of reaction in this particular time interval can be defined either with respect to reactant or can be defined with respect to product. For example, I'm defining average rate of reaction with respect to reactant. What I'll be writing? I'll be writing change in the concentration of reactant. Change in the concentration of reactant, which will be final concentration of reactant minus initial concentration. Final concentration of reactant minus initial concentration of reactant divided by time interval. And the time interval here is T2 minus T1. Simple. Time interval here is T2 minus T1. As simple as that. Right? Now you tell me one thing. I've already told you that C2 is less than C1. My dear students, if C2 is less than C1, the difference between these two, will it come out to be positive or negative? I would say C2 minus C1, it will come out to be negative for sure, right? But have you ever heard that rate comes out to be negative? What is rate? Speed. Is the speed negative? Speed cannot be negative. Rate cannot be negative, right? But here it's coming out to be negative. So in order to make it positive, I'll be starting with the minus sign. So that the minus which we get from here, that minus and this minus, finally it makes it positive. Perfect. So this is how you write the average rate of reaction with respect to what? With respect to reactants. Perfect. Now, if I ask you, what about the average rate of reaction with respect to products? In the same time interval, you can calculate the average rate of reaction, but with respect to products, yeah, it's going to be change in the concentration of products, which is final concentration of product minus initial. Final is C3, initial is 0, divided by time interval is T2 minus T1. Time interval is T2 minus T1, and this value automatically, it will come out to be positive only. So is there any need to multiply with minus? No, there is no need to multiply with minus. Instead, you can write plus here. Okay, right? I hope this is again super clear to everyone. So my dear students, just try to understand one thing. Average rate of reaction can be defined either with respect to reactants or with respect to products. You just have to do one thing. Change in the concentration of reactants divided by time interval, or change in the concentration of products divided by time interval. That's it. Okay, that's it. Now people, one more thing. What is the significance of this negative sign and what is the significance of this positive sign? This negative sign, first of all, signifies, this particular negative sign, it signifies that we are measuring the rate of reaction with respect to reactants. This negative sign, first of all, signifies that we are measuring the rate of reaction with respect to reactants. Yeah? Okay? And at the same time, the same negative sign signifies that the concentration of reactants decrease with time. The same negative sign signifies that the concentration of reactant decrease with time. In the similar way, this positive sign over here, it first of all signifies that we are calculating rate of reaction with respect to what? With respect to products. And this positive sign also signifies that the concentration of product, it increases with time. So I hope you got to know why I mentioned positive and negative here, right? That means whenever you want to calculate the average rate of reaction with respect to reactants, you'll be starting with a minus sign. Whenever you'll be calculating the average rate of reaction with respect to products, you'll be starting with the positive sign. As simple as that. And why negative, why positive? You already know it now. Because the rate of reaction can never be negative. We always have to make it positive. Yeah? Perfect. Let's try to understand the same scenario in the form of a graph so that you get its actual feeling. Try to understand what exactly I'm going to say. Try to understand what exactly I am going to say. See guys, have a look now. I'm going to make you understand by graphical representation. For example, the reaction is again A gives B. Imagine at time T1, the concentration of reactant is C1, for example. The concentration of reactant at time T2, that's for example C2. At time T1, the concentration of reactant is C1. At time T2, the concentration of reactant is C2. At time T1, let's assume that the concentration of product is C3. And at time T2, let's assume that the concentration of product is C4. We already know the concentration of reactant decreases with time. The concentration of product, it increases with time. So can I say C2 value will be less than C1, first of all, and at the same time, C4 value will be greater than C3. This is something which is understood. Now, my dear students, in this particular time interval, which is T2 minus T1, in this particular time interval, I want to define the average rate of reaction. First of all, average rate of reaction. can be defined either in terms of reactants or you can define it in terms of products. If you are defining the average rate of reaction with respect to reactants, you'll be starting with the minus sign. Then change in the concentration of reactant. Final concentration of reactant minus initial concentration divided by time interval, which is T2 minus T1, right? Average rate of reaction in the same time interval with respect to products, which is going to be, start with the plus side, final concentration of product minus initial concentration of product divided by time interval, which is T2 minus T1, correct? This is something which we have discussed. Now, for example, the same thing I'm going to draw in the form of a graph. Same thing I'm going to draw in the form of graph. For example, I'm making a curve between concentration versus time for reactants. You know, as the time proceeds, the concentration of reactant decreases with time. For example, the concentration of reactant, we know it decreases with time. I'm selecting this particular point. Let's say this particular point represents T1. Let's assume this particular point, it represents T2. It represents T1, this represents T2. So if I ask you, what about this particular interval? What about this particular interval? This interval is going to be simply T2 minus T1. This particular interval is going to be T2 minus T1. Now, my dear students, whether this graph is for reactant or product, it's absolutely for reactant. Now tell me, at time T1, what will be the concentration of reactant? At time T1, the concentration of reactant is C1. At time T2, the concentration of reactant is, the concentration of reactant is C2. Perfect. Right? Now, from this particular graph, if you want to calculate the average rate of reaction, you can do that. Average rate of reaction. Are you calculating with respect to reactant? Yes, you are calculating with respect to reactant, which will be equal to minus times final concentration, that is C2, minus initial concentration, that is C1. So minus times C2 minus C1, and the time interval is T2 minus T1. Perfect. Right? And at the same time, my dear students, for example, I'm going to do the same thing with respect to products. Concentration versus time. When it comes to products, we know concentration of product increases with time. Now, I'm again going to mark 2 points. This is T1, for example. This is T2, right? So at T1, what is the concentration of product? At T1, the concentration of product is C3. And at the same time, at time T2, what is the concentration of product? At time T2, the concentration of product is C4. Now, if you want to calculate the average rate of reaction in this particular time interval, this particular time interval is T2 minus T1. If you want to calculate average rate of reaction in this particular time interval, how you are going to calculate it? You'll be starting with the positive sign. Then, change in the concentration of product. Final concentration of product minus initial. This is final concentration and this is initial concentration of product. So, final C4 minus initial, that is C3, divided by time interval, that's T2 minus T1. Yeah? Perfect. Right, my dear students? Sir, do you remember Shimon Joseph? Absolutely, I do remember. He's a very good friend of mine. Yeah? He's a very good friend of mine. We have started the teaching journey together from Chennai. Perfect, people. Is every single thing clear till here? Is every single thing clear till here? Yeah? So I hope you got the concept of average rate of reaction. So finally, I would want you guys to remember one thing. Average rate of reaction, you can define either with respect to reactant or with respect to product. When you are defining it with respect to reactant, you'll start with a minus sign. Then change in the concentration of reactant divided by time interval. Average rate of reaction with respect to product, you'll start with the plus sign. Change in the concentration of product divided by time interval. That's all. Nothing else. Its application part you will see in a while. But before talking about its application, there is one more thing that I would want all of you to know right now. What is that? That is instantaneous rate of reaction. Now, my dear students, how do you exactly define the instantaneous rate of reaction? How do you exactly define it? What about its definition? Let me tell you, instantaneous rate of reaction. It is defined as similar thing. The change in the concentration of either reactants or products in a very small time interval. In a very small time interval. And I'm mentioning as delta T approaching towards zero. Delta T approaching towards zero. Okay, tell me just one thing. How do you write the average speed? Average speed I'm talking about. Average speed in physics. How do you write it? You write it like this. Delta X divided by delta T. Right? Delta X divided by delta T. It represents your average speed. Perfect. It represents your average speed. Right? How do you write instantaneous speed? How do you write instantaneous speed? What you exactly do, you use the limit. Limit. Delta T approaching towards zero. Then you write delta X divided by delta T. And this is something which you represent with dx divided by dt. And this dx upon dt is something which you call as instantaneous speed. I hope you know it. I hope you know it, right? I hope you know it. Now, my dear students, in the similar way, the way you convert average speed into instantaneous speed, in the similar way, you can convert average rate of reaction into instantaneous rate of reaction. How do you represent average rate of reaction? Average rate of reaction you are going to represent like this. Change in the concentration divided by time interval. Now, if I ask you, how do we represent instantaneous rate of reaction? What you exactly do? You'll be using the limit. Limit delta T approaching towards zero. It's going to be delta C divided by delta T. Right? And this whole term, finally, you are going to represent like this. dC upon dt. dC upon dt. Perfect. dC upon dt. What kind of idea it's going to give me? dC upon dt. What kind of idea it's going to give me? Let me tell you. It gives me the slope of the tangent. It gives me the slope of the tangent at a point on concentration versus time curve. On concentration versus time curve. On concentration versus time curve. Let's try to understand this particular thing. Let's try to understand this particular scenario. Have a look, people. Have a look. For example, I'm going to make a graph. I'm going to make a graph between concentration versus time. For example, I'm making it for reactants. Or let me make it for products. Right? We know with time, the concentration of product increases. Right? We know the concentration of product increases with time. So this particular graph, it is valid for products. It's valid for products. Now, my dear students, if I choose a very, very, very small time interval, if I choose a very, very, very small time interval, that means, am I trying to define average rate or instantaneous rate? I'm trying to define the instantaneous rate. Yeah? Okay. So basically, I'm choosing a very small time interval. Very small time interval, right? Very small time interval. For example, from here to here. Very small time interval, right? My dear students, very small time interval I'm choosing. If I'm choosing a very small time interval, it looks like a point to me. Even this particular, it looks like a concentration to me, right? It looks like a point to me as well. I'm choosing a very small time interval. Now, in this very small time interval, I'm asking you to calculate the instantaneous rate of reaction. How do you calculate the instantaneous rate of reaction? Slope of the tangent at a point on concentration versus time curve. This is concentration versus time curve, right? This is concentration versus time curve. Now, at this particular point, what you'll be doing? You'll be drawing a tangent. At this particular point, you'll be drawing a tangent. You will be drawing a tangent since you have drawn a tangent, right? Slope of the tangent. How do you calculate the slope of the tangent? Slope of the tangent is going to be nothing. That's going to be tan of theta. Tan of theta. What is theta? Theta is the angle which this tangent makes with the positive x-axis in the anti-clockwise direction. So this is theta. This is your theta. Once you get theta, you can take the tan value. Tan of theta is going to give you what? Tan of theta is going to give you instantaneous rate of reaction. And my dear students, try to understand one more thing. Whether theta is acute or obtuse, the theta which we are forming here, it's acute. And tan of acute angle is always positive. Right? Tan of acute angle will be positive. Right? What does that mean? What does that mean? That means the instantaneous rate is directly coming out to be positive. So that indicates you have calculated the instantaneous rate of reaction with respect to products. Absolutely, you have measured it with respect to products, right? Yeah. Right, people? SRP, can you just leave the chats? Right? It's my complete discretion. Where do I want to teach? None of your business. If you want to study, just study here or leave. Or I have the option of blocking you as well. Yeah? I hope you get it. Okay. So my dear students, try to understand it in a different way now. Try to understand it in a different way now. For example, I'm making one more graph, which is again concentration versus time. Right? Which is again concentration versus time. Now, my dear students, if I make the graph for reactants, you know, the concentration of reactant that decreases with time. So this is how the curve will look like. This is how the curve will look like. Perfect. Now, for example, imagine I'm choosing a very, very, very small time interval from here to here. From here to here. Very, very, very small time interval. And I want to calculate the instantaneous rate of reaction in this very, very, very small time interval. I want to calculate the instantaneous rate of reaction in this very small time interval. How exactly I'm going to do it? How exactly I'm going to do it? Slope of the tangent at a point on concentration versus time curve. My dear students, at this particular point, I'm going to draw a tangent. This is the tangent, right? I'm going to measure the angle with which the tangent makes with the positive x-axis in the anti-clockwise direction. So this is theta. Once I get theta, I'm going to calculate tan of theta. I'm going to calculate tan of theta, right? I am going to calculate tan of theta. But is the theta acute or obtuse? The theta is obtuse. Or tan of obtuse will be negative, right? So tan of theta will be coming out to be negative. What does that signify you? What does that tell you? That means you have calculated the instantaneous rate with respect to reactants or products. Absolutely with respect to reactants, right? Perfect. So in short, let me tell you one simple thing which you are going to remember from now onwards. Instantaneous rate of reaction with respect to products will come out to be positive because theta comes out to be acute. Theta is acute. Tan of theta is always positive. So it's plus tan theta. It's always plus tan theta. Instantaneous rate of reaction with respect to products. But if I ask you, what about instantaneous rate of reaction with respect to reactants? Right? Is it going to be tan theta or minus tan theta? It is going to be minus tan theta. Why? Because if you only write tan theta, if theta is obtuse in case of reactants, then tan theta will be negative. But rate cannot be negative. So in order to make it positive, I'll be multiplying with minus sign over here. Right? Perfect, people? Yeah? Is this clear to everyone? So these are two more important things which I would want you guys to take a note of from now onwards. So I hope you got to know the difference between average rate and instantaneous rate. Average rate, the time interval is big. Instantaneous rate, the time interval is very, very, very small. Delta T approach towards zero. Yeah? Whenever you want to calculate either average or instantaneous rate with respect to reactant, you'll be starting with minus sign. Average or instantaneous rate with respect to product, you'll be starting with the positive sign. Right? And all the things are in front of you. Its application part, we'll see in a while. Yeah? Okay, guys? Is it clear to everyone quickly? Is it clear to everyone? Perfectly done. Now, dear students, I'm going to mention a topic, that is the rate of reaction as per stoichiometry. Rate of reaction as per stoichiometry. Rate of reaction as per stoichiometry. Try to understand few new terminologies now. For example, I have got a balanced chemical equation as N1A plus N2B. For example, it gives N3C plus N4D. This is a balanced chemical equation in which N1, N2, N3, N4, these are the stoichiometric coefficients of reactants and products respectively. Now people, we know reactants, they disappear with time. Reactants are consumed with time, right? So reactants, they disappear with time. What about products? Products, they get formed with time. They appear with time, right? So if I mention a term, rate of disappearance, the rate with which reactants disappear. The rate with which reactants disappear. I'm using the term rate of disappearance. Disappearance is the term which is used for reactants, because reactants, they keep on disappearing with time, right? Because their amount keeps on decreasing with time. So reactants keeps on disappearing with time. So rate of disappearance, for example, of A, how do I write it mathematically? Whenever you have to mention the rate of disappearance, you'll be starting with a minus sign. Right? This minus sign indicates that this A, its amount, its concentration decreases with time. Yeah? So you'll be starting with a minus sign. Then, since you are writing rate of disappearance of A, so starting with a minus sign, then you'll be writing change in the concentration of A divided by time interval. Right? Perfect. This is something which I call as average rate of disappearance of A. If you want to write it in the instantaneous form, you can write it as minus d of A divided by dt. This particular term, it represents average. This particular term, it represents instantaneous. That is the difference, nothing else. For example, if I want to write the rate of disappearance of B, B is one more reactant. Rate of disappearance, I'll be starting with the minus sign. Right? I'm starting with the minus sign. Now, it's going to be change in the concentration of B divided by time interval. Perfect. This is how you represent, this is how you write the rate of disappearance of B. Now, my dear students, should I use the term rate of disappearance for C, or I'll be using the term rate of appearance? Either you write rate of appearance or you write rate of formation. Rate of appearance or rate of formation of what? Of C. It is going to be equal. Since you are writing rate of formation, rate of appearance, you'll be starting with a positive sign. And then it's going to be change in the concentration of C divided by time interval. Right? And in the similar way, if you want to write rate of appearance or formation of D, you'll be starting with a positive sign, change in the concentration of D divided by time interval. This is how you write rate of disappearances and appearances. Okay? This is how you write rate of disappearances and appearances. I hope it is super clear to everyone. Yeah? Right? Now, my dear students, remember one more thing. If I talk about the rate of reaction, till now I was talking in terms of rate of appearance or rate of disappearance of product reactant respectively. Now, what about rate of reaction? My dear students, in a particular time interval, every reaction has got a particular rate of reaction value. In a particular time interval, every reaction has got a fixed rate of reaction value. And rate of reaction, rate of a particular reaction, since it's fixed, no doubt it's fixed, it's constant. In a particular time interval, it's fixed, right? Now, rate of reaction, how do we calculate the actual rate of the reaction? Till now, I told you how to write the rate of disappearance, rate of appearance. Now, I'm going to show you how to write the actual rate of the reaction. Actual rate of reaction is written as rate of disappearance or appearance of reactant or product divided by stoichiometric coefficient of reactant or product. For example, let's say you are trying to calculate rate of reaction. You are trying to calculate rate of reaction. You want to calculate rate of reaction with respect to A. You want to calculate rate of reaction with respect to A. In the numerator, you'll be using rate of disappearance of A because A is a reactant which disappears with time. Yeah. So rate of reaction with respect to A, it's going to be rate of disappearance of A. How do you mention rate of disappearance of A? You start with minus, then you write change in the concentration of A divided by time interval, right? Whole divided by stoichiometric coefficient of A, which is N1. Absolutely, right? Now, my dear students, finally, I can write it like this. Minus 1 divided by N1, change in the concentration of A divided by time interval, that's delta T. This particular term is something which you call as the rate of reaction. This particular term is going to give you the actual rate of reaction in the time interval delta T. Well, you can calculate rate of reaction with respect to B as well. You can calculate rate of reaction in the same time interval with respect to B as well. B is again the reactant. So again, you'll be starting with the minus sign. Now you'll write 1 divided by stoichiometric coefficient, that's N2. And over here, you'll write change in the concentration. You'll write change in the concentration of B divided by time interval, that's delta T. So this particular term is also going to give you the rate of reaction only. Since the time interval is same, so whatever rate of reaction you will be getting after solving this particular term, same is the value of rate of reaction which you get after solving this particular term, because rate of reaction is always fixed. It's always constant at a particular temperature. Yeah. Similarly, rate of reaction with respect to C. C is the product. So should I use rate of disappearance or rate of appearance? I'll use the term rate of appearance. Rate of appearance of what? Rate of appearance of C. So I'll be starting with plus 1 divided by stoichiometric coefficient of C, that's N3. Change in the concentration of C divided by time interval. Perfect. Now again, rate of reaction with respect to D, plus 1 divided by N4. Change in the concentration of D divided by time interval. Now, my dear students, in all these terms, first, second, third, and fourth, in all these terms, have a look, time interval is same. If the time interval is same, that means whatever rate of reaction will be coming after solving this term, same rate of reaction will be coming after solving this term, same rate of reaction will be coming after solving this term, same rate of reaction will be coming after solving this term, because at a particular temperature, rate of reaction always has a fixed value, right? Let me know in the charts if it is super clear to you. Quickly. Let me just give you the quick summary of what I said. I'm taking a balanced chemical equation, N1A plus N2B. It gives N3C plus N4D. My dear students, first of all, rate of reaction I can calculate with respect to A, as well as B, as well as C, as well as D. If I'm calculating rate of reaction with respect to A, I'll be starting with minus sign. 1 divided by stoichiometric coefficient, that's N1. Change in the concentration of A. Divided by time interval, that's delta T. You can calculate the same rate of reaction with respect to B. B is again the reactant, so minus 1 by stoichiometric coefficient. Change in the concentration of B divided by time interval. Similarly, with respect to C, it's going to be plus 1 divided by. What's happening with this pen? It's going to be plus 1 divided by N3. Change in the concentration of C divided by time interval. Similarly, with respect to D, it's going to be plus 1 divided by N4. Change in the concentration of D divided by time interval delta T. Right? And this particular equation which you wrote, this is something which you call as differential form of rate. Okay, differential form of rate. So you take any term, right? Take any term, solve it, you'll be getting the rate of the reaction. That's it. Right, people? Is this clear to everyone quickly? Is this clear to everyone? Quickly. Let me know once in the chats, everyone, if every single thing is clear till here. Perfect. Okay, one more thing. If I write rate of disappearance, if I write rate of disappearance of A, how am I going to write it? Whenever we will write the rate of disappearance or rate of appearance, we are not supposed to divide with the stoichiometric coefficient. Whenever you want to write rate of appearance or disappearance, you are not supposed to divide with the stoichiometric coefficient. But when you want to write the rate of reaction, at that point of time, you have to divide with the stoichiometric coefficient. Yeah? Now people, rate of disappearance of A. How? Start with minus sign, which represents disappearance. Change in the concentration of A, divide by time interval. Do not divide with the stoichiometric coefficient. This is going to give you the rate of disappearance of A. Similarly, the rate of appearance. The rate of appearance of C. How you are going to write it? Appearance you are writing. So start with plus. Change in the concentration of C. Divide by time interval. This particular term is going to give you rate of appearance of C. As simple as that. Right? Perfect. Now people, tell me the answer of this particular question. Tell me the answer of this particular question. One simple question. And you cannot believe it was asked in your NEET examination 2 years back. The reaction was like this. N2 gas plus 3 times H2 gas. It gives 2 times NH3 gas. We were supposed to write the differential form for this particular equation. Can't you write? Can't you write differential form of rate? Absolutely, you can do that. Rate of reaction with respect to N2. N2 is the reactant. So start with minus. 1 divided by. Stoichiometric coefficient is 1. So it's going to be change in the concentration of N2 divided by time interval. That's delta T. Now in terms of H2, start with again minus. 1 by stoichiometric coefficient. It's going to be change in the concentration of H2 divided by what? Divided by time interval. That's same delta T. With respect to NH3, start with a plus sign because NH3 is the product. 1 divided by stoichiometric coefficient. Change in the concentration of NH3 divided by time interval. That's delta T. Right? Perfect. Okay. This was like 2 years back. The same question was asked in your NEET examination. Okay. Now comes a point. Now comes a point. Try to understand what the point is. For a homogeneous gaseous phase reaction. Gaseous phase reaction carried out at temperature T. Rate can be expressed. Rate can be expressed either in terms of, or let me write it like this. Rate can be expressed in terms of pressure as well. What does this mean? What does this mean? Try to understand what it means. My dear students, for example, I'm taking the reaction N1A gas plus N2B gas. It gives N3C gas plus N4D gas. This is your reaction. Okay. Now, first of all, say every reactant and product has got the same state, right? Every reactant product has got the same state. So it is the example of homogeneous reaction. And every reactant product that's in gaseous phase. So I would call this particular reaction as the homogeneous gaseous phase reaction, which is carried out at temperature T. The reaction is carried out at temperature T, right? Now, first of all, as far as your ideal gas equation is concerned, you know PV is equal to nRT. This is something which all must be knowing. Can you write P is equal to N divided by VRT? Absolutely. P is equal to N by VRT. Now, P will be equal to N by V, number of moles per unit volume. We call that as concentration. So, P is equal to concentration multiplied by R multiplied by T. So, basically for gases, pressure as well as concentration, both the terms are defined. We define pressure for gas as well as we define the concentration for the gas. For gases, pressure as well as concentration, both the terms are defined. Now, rate of reaction can be expressed either in terms of concentration or you can express it in terms of pressure as well. You can express it either in terms of concentration or you can express it in terms of pressure. How exactly? Try to understand. If I write pressure of A, that's going to be equal to concentration of A multiplied by R multiplied by T. Similarly, pressure of B, that's going to be concentration of B multiplied by R multiplied by T. Similarly, pressure of C, concentration of C multiplied by R multiplied by T. Pressure of D, that's going to be equal to concentration of D multiplied by R multiplied by T. As simple as that. Yeah, you know it now. Now, my dear students, if I want to write the differential form of rate, start with A, minus 1 divided by N1. Change in the concentration of A divided by time interval. With respect to B, minus 1 divided by N2. Change in the concentration of B divided by time interval delta T. With respect to C, plus 1 divided by N3. Change in the concentration of C divided by time interval delta T. Plus 1 divided by N4. Change in the concentration of D divided by time interval delta T. Correct? Okay. Now guys, try to understand one thing. Rate of reaction can be written as minus 1 divided by N1. Delta. Concentration of A. So instead of concentration of A, can I write pressure of A divided by RT? Right? Instead of concentration of A, I can write pressure of A divided by RT, whole divided by what? Whole divided by delta T is equal to minus 1 divided by N2. Delta of concentration of B is going to be pressure of B divided by RT, whole divided by delta T is equal to plus 1 divided by N3. Plus 1 divided by N3. Delta of concentration of C is going to be pressure of C divided by RT, whole divided by delta T. Right? Similarly, in terms of D as well. I do not have space here. That's why I'm leaving D aside. Now, guys, I can write it further like this. Since you know, this reaction is carried out at constant temperature. So, temperature is constant, R is already constant. So, they will come out of the delta. So, it will come out to be like this. Minus 1 divided by N1. Minus 1 divided by N1. RT will be in the denominator. It's going to be change in the pressure of A divided by time interval, which is equal to minus 1 upon N2. RT will come in the denominator. It's going to be change in the pressure of B divided by delta T. Similarly, plus 1 divided by N3. It is going to be change in the pressure of C divided by delta T. Same thing in terms of D as well. So RT everywhere, it will get cancelled out. And when RT gets cancelled out, you get the final expression minus 1 upon N1, change in the pressure of A divided by time interval, which is equal to minus 1 divided by N2, change in the pressure of B divided by time interval. You can write it in terms of C as well, plus 1 divided by N3, change in the pressure of C divided by time interval. You can write it in terms of D as well, plus 1 divided by N4, change in the pressure of D divided by time interval. Right? Perfect. That's something which I already told you. For a homogeneous gaseous phase reaction, rate can be expressed either in terms of concentration. It can be expressed either in terms of concentration or it can be expressed in terms of pressure. Now, one thing which you have to remember here. What is that? One thing which I want you guys to remember. Whenever you are using these terms to calculate rate, at that point of time, you are calculating rate in terms of moles liter inverse. Let's assume time is in seconds. So second inverse. If you are using, for example, this particular term to calculate rate, so in the numerator you have got concentration, in the denominator you have got time. Concentration units will be moles per liter, time units, for example, seconds. So moles per liter per second, right? If you are using this term, or you are using this particular term, or you are using this particular term, or you're using this particular term. So you are calculating basically the rate of reaction in terms of moles per liter per second or moles per liter per minute, whatever, right? But if you are using this particular term to calculate rate, or you're using this particular term to calculate rate, or you're using this particular term, or even you are using this particular term, in the numerator you have got pressure, in the denominator you have got time, right? So basically you are calculating rate in terms of, let's say pressure is in ATM, so it's going to be ATM. Let's say time is in seconds, so it's going to be an ATM second inverse, or ATM minute inverse, ATM hour inverse, bar minute inverse, bar second inverse. This is all yours, right? Is every single thing clear till here? Quickly. Quickly, guys. Yeah? Perfectly done. So, whenever you are supposed to calculate rate of reaction in terms of moles per liter per second, take any term out of these terms. Whenever you are supposed to calculate rate of reaction in ATM second inverse, for example, take any term out of these terms and get the rate of the reaction. Now, let's try to utilize all these concepts in the questions. But before solving the questions, let me know everyone in the chats with yes or no, so that I'll get to know whether you got the concept or not. Quickly. Yeah? Let's try to use all these concepts in the questions so that you can understand it properly. The first question which is on your screen. The first question which is on your screen. If the concentration of H2O2 changes from 0.5 molar to 0.05 molar in 15 seconds, then calculate rate of reaction, rate of appearance of O2. Two things we have to calculate. See, these sort of questions frequently you would have seen. Now, first of all, I'm given with a balanced chemical equation. Can I write the differential form of rate? Write with respect to H2O2. Start with minus sign. 1 by stoichiometric coefficient, that's 1. Change in the concentration of H2O2 divided by time interval delta T. In terms of water, water is the product. So start with plus 1 by stoichiometric coefficient. Change in the concentration of H2O divided by time interval, that's delta T. Now, O2, which is the product, start with plus 1 by stoichiometric coefficient. So 1 divided by 1 by 2, which makes it 2. Change in the concentration of O2 divided by time interval delta T. So first I wrote the differential form of rate. Okay. Now, my dear students, try to see what is given to us. The concentration of H2O2 changes from 0.5 molar to 0.05 molar in 15 seconds. So time interval is 15 seconds. Time interval is 15 seconds, right? Let's try to calculate the rate of reaction. Rate of reaction can be either calculated by solving this term, or by solving this term, or by solving this term. Now, which term I'll take out of the three? The one whose data is given. The data for H2O2 is given. So I'll take the first term and try to solve this. Done and dusted. So it's going to be minus times change in the concentration of H2O2, which is going to be final concentration of H2O2 minus initial concentration of H2O2 divided by time interval is 15 seconds. Now solve it. The answer is going to be in moles, liter inverse, second inverse. This is the rate of reaction. This is the rate of reaction. Yeah. Perfect. Perfect, people. This is the rate of reaction. Okay. Number one. First question is done and dusted. What about the second question? Calculate the rate of appearance of O2. First of all, how do I mathematically denote rate of appearance of O2? Rate of appearance of O2. How do I denote it? Rate of appearance of O2. I'll be starting with a positive sign. Whenever I will have to calculate rate of appearance of disappearance, do I need the stoichiometric coefficients? No way, right? It is simply going to be change in the concentration of O2 divided by time interval. This is something which you call as the rate of appearance of O2, which you are supposed to calculate, right? Now, my dear students, in this particular differential form, The data for H2O2 is given. The data for O2 is to be calculated. The data for H2O2 is given and the data for O2 is to be calculated. Just try to equate these two terms. That's it. Just try to equate these two terms. It's going to be minus delta H2O2 divided by delta T is equal to 2 times delta of O2 divided by delta T, right? Now from this particular equation, can I write something like this? I write delta O2 divided by delta T first. Delta O2 divided by delta T is equal to this 2 will be here in the denominator. So it's going to be minus 1 divided by 2 and you're going to write delta of H2O2 divided by delta T, right? Perfectly done. So this delta O2 divided by delta T, is this something which we call as the rate of appearance of O2? Absolutely. Rate of appearance of O2 will be equal to minus 1 by 2 change in the concentration of H2O2, which is equal to final concentration of H2O2 minus initial concentration of H2O2 divided by time interval, that's 15 seconds. The answer is going to be in moles later inverse, second inverse. So both equations are done and dusted. Simple. Correct? Correct, guys? Is every single thing clear till here? Just give me a second. Just give me a second, guys. Perfectly clear? All right. So let's try to solve a few more questions. Let's try to solve a few more questions. Look at this particular question. If the rate of appearance of O2 is 0.5, rate of appearance of O2. First of all, in this particular reaction, how do you write the rate of appearance of O2? Rate of appearance of O2 is equal to, I'll be starting with the plus sign. Change in the concentration of O2 divided by delta T. This rate of appearance of O2. And this rate of appearance of O2 is given to me as 0.5 moles later inverse, second inverse, right? Calculate the rate of disappearance of N2O5. How do I represent the rate of disappearance of N2O5? Rate of disappearance, you'll start with minus sign, right? Change in the concentration of N2O5 divided by delta T without dividing by stoichiometric coefficient. This term is called as rate of disappearance of N2O5. Okay? And this particular term, the rate of disappearance of N2O5, we have to calculate this term, right? We have to calculate this term. Now, my dear students, the reaction which is given to us, it is given to us in balanced format. The reaction is given to us in balanced format, right? Now, what I'll be doing, just write the differential form of rate. Rate of reaction is equal to, in terms of N2O5, start with minus 1 by stoichiometric coefficient. Change in the concentration of N2O5 divided by delta T. Similarly, with respect to N2O4, start with plus 1 by stoichiometric coefficient. Change in the concentration of N2O4 divided by delta T. Similarly, it's going to be plus 1 by stoichiometric coefficient, that's 1. Change in the concentration of O2 divided by delta T. Correct? So all these terms are going to give me the rate of reaction. All these terms are going to give me the rate of reaction. Okay? Now, which two terms among these three I'm going to take? Which two terms among these three terms I'm going to take? The data for O2 is given. The data for N2O5 is to be calculated. Right? The data for O2 is given. The data for N2O5 is to be calculated. So I'm going to relate these two terms, nothing else. So I'm going to write minus 1 by 2, change in the concentration of N2O5 divided by delta T is equal to plus delta O2 divided by delta T. Right? Now, what exactly? Delta O2 divided by delta T. What do I have to calculate? I have to calculate minus delta N2O5 by delta T. So, take this 2 from here. And multiply this term with 2. That's it. I mean, just cross multiply things. Nothing else. Just cross multiply things. The 2 which was here in the denominator, that 2 goes here. This was plus, multiplied with 2. Right? Now, 2 I'm writing as such. Delta O2 by delta T is given, I believe. That's 0.5. So the value comes out to be 1. And it's going to be mole, liter inverse, second inverse. So what is this term? What did we calculate? What did we calculate? We calculate the value of this particular term. And what do we call this particular term as? This is called as the rate of disappearance. This is called as the rate of disappearance. Rate of disappearance of what? Rate of disappearance of N2O5. Right? Is it clear? Is it clear, people, quickly? And this was something which I was supposed to calculate. That's all. Look at this particular question. Look at this particular question. Try to solve this as well. We are given with a reaction. For the following reaction, calculate the rate of reaction in the time interval 5 to 15 seconds. Time interval 5 to 15 seconds. So this is the time interval. This is the time interval, which I'm representing with delta T. So delta T, let's call this as T1. Let's call this as T2. So time interval is T2 minus T1. So 15 minus 5 comes out to be 10 seconds. So in 10-second time interval, we have to calculate the rate. Right? In 10 seconds of time interval, we have to calculate rate. Now, first of all, try to understand. The graph is between concentration versus time. And the concentration is decreasing with time. So this graph has to be for the reactant. Because we know concentration of a reactant decrease with time. And in the reaction, which one is your reactant? It's NH3 which is your reactant. So this graph has to be for NH3. This graph has to be for NH3. What are we supposed to calculate? Calculate the rate of the reaction in this particular time interval. So let me calculate rate of reaction with respect to NH3. NH3 is reactant, so start with minus 1 by stoichiometric coefficient. Change in the concentration of NH3 divided by time interval, that's delta T, right? Now the question is done and dusted. So minus 1 by 2, change in the concentration of NH3. That's going to be final concentration of NH3 minus initial concentration of NH3. Final concentration of NH3 is 0.2. Initial concentration is 0.6 divided by time interval is 10 seconds. Now solve it. Get the value of the rate of reaction. That's all. That's something which we're supposed to calculate. That's it. Nothing else. Isn't it simple, people? Isn't it simple? One more question. One more question. It might look difficult to you, but it's not difficult. Try to understand. For the reaction, there are some parameters which are given. Find the relation between K1, K2, K3. Reaction is also given. How? How you are going to get the relation between K1, K2 and K3? See guys, it's also simple. The reaction which we are given with, just write the differential form of rate with respect to N2O5. Start with minus, right? Change in the concentration of N2O5 divided by time interval. Now here we are not using delta, so I'm not also going to use delta. I'll use D for example. So it's going to be minus D of just a second. What did I do? Okay. All right. Okay. So write the differential form of rate. It's equal. Start with minus because you are going to write with respect to N2O5. So it's D of N2O5 divided by dt, which can be also written as plus 1 divided by stoichiometric coefficient. It is D of NO2 divided by dt, which can be written as plus 1 divided by stoichiometric coefficient, that's 1 by 2. So 1 by 1 by 2 makes it 2, D of O2 divided by dt. This is how you wrote the differential form of rate. This is how you wrote the differential form of rate. Now guys, tell me this minus D of N2O5 by dt, minus D of N2O5 by dt, that's given to me as K1 multiplied by concentration of N2O5, right, is equal. Plus 1 by 2 I'm writing as such. Now plus D of NO2 by dt, plus D of NO2 by dt, that's given to me as K2 multiplied by concentration of N2O5, which is equal to 2 times d of O2 by dt. D of O2 by dt is also given to me. That's K3 multiplied by concentration of N2O5. So all these parameters are basically given to me as the equation, right? So can I say this N2O5, N2O5, N2O5 got cancelled out. So the value is K1 is equal to K2 divided by 2, which is equal to 2 times K3, right? Now look at the denominators. 1 to 1. The LCM of denominator will be 2. LCM of denominator will be 2. So multiply throughout with the denominator. So this will be 2 times K1. This will be K2. This will be 4 times K3. Right? This is the relationship between K1, K2 and K3 which you were supposed to calculate. Is it clear? Is it clear, people? Quickly, let me know in the chats. Is it clear? Yes? Perfect. Okay, tell me whether this question you can do on your own. It is a similar type of question. Calculate rate of reaction in moles per liter per second and ATM per second. Can you solve this question on your own? Can you solve the question on your own? Yeah? Quickly, quickly. You sure you can watch it? Absolutely. There is no issue. Perfect. Let me give you one more question. Just a second. For example, the question is like this. X times A gives Y times B. X times A gives Y times B. It is given that, just a second. It is given that minus log of dA divided by dt is equal to log of d of B divided by dt plus 0.3 plus 0.3. Find the value of X and Y. Can you give it a try? Can you solve this question? You should be, I believe. You should be able to solve this question. See guys, we are supposed to get the value of X and Y, correct? The reaction that's given to us, that's XA gives YB. Can you write the rate of reaction with respect to A? It's going to be minus 1 divided by X, change in the concentration of A divided by dt. Write the rate of reaction in terms of B. It's going to be plus 1 divided by Y, change in the concentration of B divided by dt. Let me call this as equation number 1. Okay. Look at this particular equation. It is minus times log of d of A divided by dt is equal to, this is log of, or just have a look. Wait, just have a look. See guys, this term is in log, this term is in log, and this term is not in log. Can you make this term in the logarithmic form? Can you write this particular term in the logarithmic form? So instead of 0.3, you can write log of 2. Because you know, log of 2 to the base 10, that's 0.3 only. Log of 2 to the base 10, that's 0.3 only, right? Now it is the log of m plus log of n, which is going to be log of m into n, right? So log of 2 multiplied by d of B divided by dt. Correct? So if I take nt log on both the sides, if I take antilog on both the sides, it has to be minus d upon a upon dt, which is equal to 2 times d of b divided by dt. Or this 2 you can take here. It's going to be minus 1 upon 2 d of a divided by dt has to be equal to d of b divided by dt. Perfect. Look at this particular equation now. Just compare these two equations. Just compare these two equations. My dear students, when you compare these two equations, you will be getting the value of x as 2 and the value of y as, this will be 1 by 1, right? The value of y you got to know as 1. And these were the things which you are supposed to calculate. I hope this is clear. Yeah? Is it clear? I did nothing. See, this was in logarithmic form. This was in logarithmic form. And over here, it was given as 0.3. 0.3, I converted it in the logarithmic form, right? 0.3 is nothing. That's log 2, basically. Then log of m plus log of n, which is the log of m into n, right? Multiplying both sides by the antilog, taking antilog on both the sides, it'll be log will get cancelled out. It'll be minus d upon dt is equal to 2 times db upon dt. This 2, I'm taking the denominator. I got this equation. This equation already I had formed. If I compare these two equations, I'll be getting the value of x as 2, the value of y as 1. That's it. Right? Similar type of question I'm giving you, and you are going to write me its answer in the comments. The question is x times a gives y times b. And I'm giving you minus log of d of a divided by dt. Guys, just a second. I think there was one mistake which we did. This is not minus here. Just a second. This is not minus here. It is minus here, basically, okay? It is minus here. Then when you take the antilog, right? Then it becomes minus d upon dt. So do the correction. It was not minus outside. It was minus inside, right? It was minus inside. Okay, it was minus inside. All right. So it's going to be log of minus d of a upon dt is equal to log of d of b upon dt plus 0.6. This was given data. It was given data. We are supposed to get the value of x and y. Right? X and y you are supposed to calculate. Clear? Can you do it? Yes? Will you be able to solve this question? It's simple now. Can you give it a try? Quickly, guys. No, Niranjan, it's not deleted yet. Okay, you have to follow the old syllabus only for NEET as well as JEE. Is it 3 and 1 or 4 and 1? See, 0.6 is log 4 basically. Log 4 is 0.6. Log 4 is 0.6. Okay. So give this question a try, guys. Okay, and let me know its answer in the comments. And I think I'll end the session right here only. Okay, because my head is, I don't know why it's aching. Okay, so what is day after tomorrow? Saturday. So Saturday at 6 p.m. we'll have kinetics part 2. Okay. Saturday at 6 p.m. we'll have Saturday's day after tomorrow, kinetics part 2, in which we shall be discussing law of mass action, rate law, order, etc., etc. So this session, now it's going to take 3 sessions, including this one, right? I thought to take this session for like 3-4 hours, but suddenly I am going to end this. Okay? Perfect. But day after tomorrow, on Saturday, we are going to resume from here. Is that cool? Okay, and give this question a try. Do let me know its answer in the comment section afterwards. Right? You take care, guys. God bless you all. Bye.